Okay, so this is a project that I did with my two advisors, Martin Bauer and Tom Needham, who have already left, and Nicolas Sharon from University of Houston. So before talking about my framework, let me talk about what optimal transport was about. But it's probably everyone already knows, but it's good to make sure the working. Oh, okay. No. Oh. Oh, okay. I guess it was blocked my computer. Okay, so yeah. The problem is that we suppose that we have two probability distributions on some space omega. So it would look like this. So yeah, we have red distributions and blue distributions on some 1D space. And what we are trying to do is how do we transport blue distribution to red distribution while minimizing some cost. So yeah, we want to. Oh. Okay. Yeah. Okay. So yeah, and yeah, we want to move or morph the blue distribution to red while minimizing some cost. So there are many ways to set up the cost. Yeah, but if the cost of transporting 1 unit of mass from the point X to Y is the distance between X and Y to the power of P, then the optimal cost 1 over P is called the Wasserstein-P distance between the two distributions. So you can measure you can compare the two distributions by Wasserstein distance. Now, what we will focus on in this talk is going to be what's called the dynamic formulation of optimal transport. So what would be like the opposite of the dynamic formulation is what's called the static formulation of optimal transport. And in the static formulation, we will find what's called the transport plan. So the transport plan is what's shown here, and it tells you how much mass goes where. So in this figure, it's telling you that the 50% of the blue mass should go to the left, and the other 50% should go to the right. So it's telling you how much mass should go where. And on the other hand, in the dynamic formulation of optimal transport, we will find the execution of the transport instead of the plan. So what I mean is that we will find a snapshot of the distribution at each time t of the transport. So the end result would look like something like this. Yeah. So yeah, you'll find the dynamic movement of the transport at each time t. This is what we will focus on in our talk. So we will find we are interested in the snapshot of the distribution at each time t during the transport. Okay, now why do we want to care about the dynamic optimal transport? Because dynamic OT directly interpolate between distributions. So here's the example. So those are Monge and Kantrovich pictures, and these are grayscale images. And the grayscale images can be seen as some kind of distribution. So like, for example, the white pixels can be seen as like high value of distribution, and black pixels can be seen as a lower value of distribution. So now since those grayscale images can be seen as a distribution, we can interpolate those grayscale images using optimal transport. And this was the result in the paper in 2014. Now, okay, so in other words, it is one way to obtain a geodesic between probability distributions. This is not the only way to find the geodesic, but it is one way to find the geodesic. Okay. All right, so another thing that we will use is what's called the unbalanced optimal transport. So in classical optimal transport, as we have been discussing, they can only interpolate probability distributions. Now, there are cases where we want to deal with like distributions of unequal total masses, especially in biological applications, because for example, if you have cell populations, there's birth and death processes, and the total mass, total population is not always the same. So yeah, unbalanced optimal transport allows creation or destruction of mass during transport to interpolate distributions of unequal total mass. And there are formulations, there are many formulations of unbalanced optimal transport, but one of the first is the Wasserstein-Fisher-Rao distance proposed by Shizar, Perret, Schmitzer, and Diarra in 2016. Okay, now here is the mathematical formulation of the Wasserstein-Fisher-Rao. So the Wasserstein-Fisher-Rao distance measures the distance between two positive random measures. And then we will find this by solving this optimization problem. And yeah, before going into the optimization problem, let's see the notation. So here, rho tx is the distribution at time t. So that's the snapshot that we have been discussing earlier. And the omega is the momentum vector field. So it's of the transport. So it's velocity times the mass field. Now, okay, so the last one is the scalar field of mass creation or destruction. So if it's positive, we are creating mass at time t and this space x, and then if it's negative, we are destroying mass. Okay, now, so this is the optimization problem we are solving, and the first part is the kinetic energy of the transport. So it penalizes the physical movement of the transport, and just like in the usual Wasserstein setting. So the other part, called the Fisher-Rao energy, is sort of like a kinetic energy for the mass change rather than the mass movement. So yeah, it penalizes the mass creation and the destruction. Now we also have this delta squared, which will work as which will control how we balance the creation, destruction, and the transport. So if delta is large, so if delta is large, creation or destruction is more penalized. So it means that the transport is doing transport is more economical. Yeah, and finally, the equation in red is this right here, is a generalized mass conservation law. And for the Wasserstein case, where there is no mass creation for destruction, the zeta right-hand side will be 0. So yeah, this, by having zeta right here, we allow the creation of mass or destruction inside the mass conservation equation, and we can do interpolation between unbalanced total masses. Okay, so now let's talk about our framework, the path-constrained unbalanced optimal transport. So yeah, on top of the mass conservation constraint, what we are going to do is to add another additional constraint. So this is not really a new idea, since there has been already an attempt on it. So for example, you can prescribe the total mass at each time t, which is called the total mass constraint. And so the special case of this, where we prescribe the total mass at each time t to be 1. So if you set the distribution at each time t to be probability measure, it will be called the spherical Hellinger-Kantorovich distance, which was considered in 2019. But yeah, you can in general prescribe the mass to be any value, and that's a total mass constraint. And another example is more geometric, and it's called the convex set constraint. So classical result in convex geometry is that the measures on the sphere satisfying this constraint. So you multiply by x and then integrate it over the sphere, and it becomes 0. So this the measures on the sphere satisfying this constraint has one-to-one correspondence with convex sets. So what this implies is that by interpolating the measures on the sphere, you can also do the interpolation of convex sets. So we can now, not just measures, we can also do interpolation of convex sets by doing optimal transport. And in the balance case, it was considered in 2021 paper by Pierron and Charon. But yeah, here we will consider unbalanced case. And the difference is that we can deal with convex sets with the unequal total area. So the total mass corresponds to total area of the convex sets. And the last inequality, the constraint. Oops, that was a spoiler. Yeah, so the last constraint is pretty intuitive. So it's called the barriers constraint. So here we will disallow the existence of mass under in certain region. So you cannot go through the barrier, so you have to go around. Now, all those three constraints can be seen as a special case of a general constraint, which is called the affine constraint. Now, how do I see those constraints as a affine constraint? So for example, total mass constraint, you can simply just set H to be always equal to 1, then yeah, the left-hand side becomes the total mass. So you can prescribe the total mass. And for convex set constraint, I think it's straightforward. You just set H to be X and the HFT to be identically 0. And finally, for barrier constraint, you can set H to be supported on the barrier and FT to be 0. By doing this, if there's any barrier, if there's any mass on the barrier, then the left-hand side becomes non-zero, whereas right-hand side becomes 0. So yeah, it will disallow mass on the barrier. So assuming that H is positive on the barrier. Okay. So those are what we'll consider. So the first theorem that we have proved is the existence of minimizers. So let's say we have this constraint, and I don't mention here, but we will fix the initial and the terminal measure. So let's say H is continuous. So that's only one technical assumption. And then if there is a finite energy path connecting initial condition and initial measure and the terminal measure, then there is also a minimal energy path. So now what is energy? So energy is what we discussed earlier. So and the path here means the triple of rho and omega and zeta, satisfying the continuity equation and the constraint. So as long as there is a finite, as long as there is a path that makes the objective finite, then there is also a minimizer. So we to show that there is a minimizer, you just need to find the finite energy path. I will omit the details, but we can show the existence of finite energy paths for constraints we have seen. Okay, now how do we prove this? So it is pretty much the we adapting the argument for the unconstrained case, which was the paper that in 2016 we have discussed earlier, to our constrained case. So the core theorem in this argument is what's called the Fenchel-Rockafellar strong duality. So yeah, I mean, it basically says that the infimum of optimization problem or primal problem is equal to the supremum of the dual. So yeah, it's a strong duality, but there is more to it. And if the right-hand side, the supremum of the dual is finite, then it implies the existence of minimizer for the dual problem. Okay, so yeah, we will construct a primal problem so that the dual is our constrained Wasserstein-Fisher-Rao problem. Then once we have this, then as long as right-hand side is finite, the second statement of the theorem gives you the minimizer. So that's that's basically how the argument goes. And then that's, yeah. And after that, we can, so significant portion of the paper is devoted to find the finite energy path, but yeah, it's pretty technical, so I'm gonna omit this. Okay, so another theoretical part is what's called the Otto Riemannian submersion. This was already discussed by Dr. Klaas Modin last week, but the Wasserstein distance, the complicated geometry, lifts to the diffeomorphism group with the L2 metric by the Otto's Riemannian submersion, which is shown in the left column. So the result by Galway and Biala in 2017 is that there is something similar for the Wasserstein-Fisher-Rao distance. So here at the top space is top space is what's called the automorphism group, and it is a automorphism group over a cone of over omega, and it is a cone over a positive real number. And the automorphism group means that it's a diffeomorphism that is equivariant over action of real number over the cone. Yeah, so the paper in 2017 shows that there is a Riemannian submersion from automorphism group to the Wasserstein-Fisher manifold. Now, to get our version of Riemannian submersion, we will simply restrict this Riemannian submersion to our constraint space. So for the bottom, we will just restrict the space of smooth positive densities to this the space of smooth positive density with this constraint. Now, on the top space, we will use the preimage of this space by the Riemannian submersion right here. Yeah, we will just restrict the Riemannian submersion so that it will give me the Riemann submersion for our space. And by using this, we have figured out some kind of Monge formulation for our constraint Wasserstein-Fisher problem, but yeah, that's another story. Okay, now let's see the numerical results. Okay, let's first see the numerical algorithms. So we want to minimize the discretized version of the sum of the energy plus the constraints, indicator for constraints. So here, iota here, right here is a function that is 0 on the constraint and the plus infinity otherwise. So it's called the convex indicator. And this can be seen as a sum of convex functions where f and g are not necessarily smooth. So if it's smooth, then gradient descent should work well, but it's not smooth. So what's usually used in this kind of case is what's called the proximal splitting algorithm. And so there are many proximal splitting algorithms, but especially we will use what's called the Douglas-Rushford algorithm. Okay, which was also used in the original Wasserstein-Fisher paper. Yeah, so okay, so we will see total mass constraint. So the first one is I will test unconstrained Wasserstein-Fisher-Rao, and the second one is total mass constraint with ft equals 1, and the last one is total mass constraint with some kind of quadratic function. So the second one is, as we discussed earlier, it's what's called this spherical Hellinger-Kantorovich case. Okay, so this is a total mass, and for the unconstrained case, it shrinks and it grows. And for the second one, where we constrain the mass to be always 1, it's almost always 1. But this is somewhat of an approximation algorithm, so the constraint is not always satisfied. Theoretically, it should be satisfied, but yeah, this algorithm does not get you the theoretical best solution. And the last one, it's a quadratic function, so it's working well. And so here is the geodesic. So the top one is the unconstrained one, and the middle is the ft equals 1. The last one is the increasing quadratic one. So now, so the green curve is a source term, which accounts for the mass creation of destruction. So you can already see the difference between those three. So at the top, the mass is decreasing. So it's like slightly below the 0. And for here, its mass is actually increasing, which is consistent with what we have seen. And okay, so here you can see the difference in the amount of mass. So the top is the least, and the bottom is the most. And the last, this is the last, and it's like the opposite. The top is increasing and the bottom is decreasing. So yeah, you can see the effect of constraints on the parameters. Okay, so there is another constraint, so which is called moving barrier constraint. And as you can see, it's the mass is going around the barrier to get to the other side. So here's the result. Yeah, as you can see, the mass is correctly moving around the moving barrier to get to the other side. Okay, so that's about it. So in future, I would like to work on inequality constraints or another deep learning algorithm or static formulation. Okay, thank you for listening.